So in the troposphere, the majority of the air is nitrogen that doesn't affect us. It doesn't help us. It doesn't hurt us. When nitrogen N2 does affect is for diving. So when you go in deep sea, diving, this coming out of or coming into the region of the atmosphere that has a mixture of nitrogen, that you end up having nitrogen dissolved into your blood when you basically change the nitrogen concentration too quickly, and then nitrogen ends up in your joints, and it's extremely painful. So I don't know if anyone dives and is aware of that. It's called the bends, but that this nitrogen really doesn't do anything to your bodies. You inhale it, you exhale it, it doesn't do anything, except for if you're a deep sea diver and you come out too quickly. So this is what we care about, is the 21% oxygen. And we're going to be doing a lab where we do some combustion reactions. So oxygen is needed for life. And it's also needed for combustion reactions. And combustion reactions are fire. Okay, so that's what human metabolism is. Basically, it's very similar to combustion reactions, which are fire, except for your metabolism is there's no fire going on in your body, but the reactions are very similar as fire, which are combustion reactions. Okay, and so that is all going on in the troposphere. We have oxygen, we're breathing in oxygen, and we exhale that carbon dioxide. So as I mentioned in the video, we'll get to carbon dioxide concentrations, which are much lower than 1%. So the remaining 1%, about 1%, are those other gases. And a percentage, 0.04% of those other gases are the carbon dioxide, that are the carbon dioxide concentrations that cause global warming and climate change. So we're going to get to all of that, talking about all of that in the troposphere. But this is all of the regions of Earth's atmosphere. And this includes everything going from 0 kilometers out to outer space. Okay, so that's answering some of these questions, is all of those regions. So this is why I'm focusing on this, is because it's an intro to talking about the air in the troposphere, but also it's an important lesson in how to look at a graph. So this is information on a graph. Now this is a graph that is presented as a 3-dimensional graph. It's more like a cube, right? So, but when looking at a graph, you want to start by looking at the x-axis and the y-axis. So the x-axis is this temperature is on the x-axis, okay? And then on the y-axis, this is the up and down. The y-axis is the altitude in kilometers. And so understanding exactly what you're looking at when you're looking at information on a graph is one goal of Chem 9 that is outside of the sustainability, outside of the chemistry, but something for every citizen to understand the information that's presented on a graph or on a table. And so that's also going to be a running theme throughout Chem 9, is looking at information that's given to you. And this can be on a table, like on a bank statement, often gives graphs, or if you're looking at a table of data, like you're looking at the airport and you're trying to figure out when your flight is leaving and what the gate is. Looking at information on a graph or a table is a goal. Okay, so looking at this, the first question is, what is the altitude range of the troposphere? Okay, so we know that the altitude range is this y-axis. Okay, so it's the question is asking for the range. So not just one number, but an altitude range is of the troposphere. So focusing in on here, this is the range from 0 to 11. Now you don't want to just write 0 to 11, because 0 to 11 are number values, and those number values need a unit. So not just 0 to 11, but also km, that's kilometers. Okay, so you need the kilometers units in there, that's km. How about the temperature range of the troposphere? So the temperature range, let me choose a different color. Actually, blue will be good. The temperature range is on the x-axis. Don't want that. Go back. My hand just made this all move. Okay. So the temperature range is on the x-axis, and this is the troposphere x-axis is in red. So this is going from this number negative 52 degrees Celsius in red to here, and they didn't give us this number that ends here for the red, and that's for the region of the troposphere, that red line. So we can start with the negative 52 degrees Celsius, and it ends to just a little bit above zero. So this is on here, this line is in between, it looks like 0 and 10, so maybe about 3 degrees Celsius, somewhere close to 0. So 3, 5, but that they didn't give us the number there. They did give us the number for that one. And is that 3? Hold on a second, let me erase this. So dropping this down, this is actually -3. No, that's different. Okay. All right. So this is because I'll focus again, there's no number given here. So it's just a little bit over 0 in degrees Celsius. So you can see that those are also the units, which are degrees, that little circle, and Celsius are the units of temperature. So which region has the largest temperature range? Okay, so this is not going to be a number, but just find the largest temperature range, which is the x-axis, which it appears to be this wide amount of numbers from -93 to 172. This is that region called the thermosphere. Okay, and that is actually why it's called the thermosphere. The thermosphere has the largest temperature range, the thermal range. That's why it's called the thermosphere. And so it's from -93, this dot, to 1,727. So -93 degrees Celsius to positive 1,727 degrees Celsius. So that's a very large range, and you can see that on the graph and also from the numbers. Which region has the smallest temperature range? Okay, so the smallest temperature range, you can see that the options are, we can throw out the thermosphere, the exosphere, they didn't give us any range, the mesosphere, stratosphere, and troposphere. So let's compare the mesosphere, stratosphere, and troposphere. Okay, so versus the 3 that are remaining. Let's list those to decide. Okay, so we know that the troposphere is already listed as -52 degrees Celsius to 3 degrees Celsius. Okay, what's the mesosphere range? So again, on the x-axis, the mesosphere is this range that is this red line that goes from -93 to -3. So -93 degrees Celsius to -3 degrees Celsius. And then the stratosphere, you can see, is -52 to -3. Okay, so -52 degrees Celsius to -3 degrees Celsius. So of these 3, which one is the smallest range? Okay, so don't be fooled by this is -52 to +3 compared to -52 to -3. Okay, so which one is smaller? This one is actually slightly smaller than the troposphere by about 6 degrees. Okay, this is about 90 compared to about 50 on the other 2. Okay, so the region that contains the ozone layer, going back to here, is you can see that ozone layer is in this region called the stratosphere. And so I mentioned that we're going to be talking about the ozone layer. Ozone is a gas that is in our troposphere, and when ozone is in the troposphere, it's unhealthy. But when ozone is up there in the stratosphere, we need that ozone in the stratosphere. The ozone layer protects all of Earth and all living things, including us, from harmful UV radiation. So we're going to get to how that works in the next module. So, but it protects everything on Earth from harmful UV radiation. And then the last question, what is the altitude range of the stratosphere? Okay, so we got to look for the stratosphere, and the altitude range is on the y-axis. So here's the stratosphere, and the altitude range on the y-axis is this 11 to 48. So we want to write the range, not just a single number, but the range, which is 11 to 48. And then the units are still going to be kilometers for the altitude. So as long as you understand what these units mean, this is percent, this is parts per million or ppm, and this is parts per billion or ppb. Actually, I want to put on here, this is 2.1 lecture worksheets. Okay, that if you understand what these units mean, these are words, percent, parts per million, parts per billion, but these are also units of concentration. Okay, so these are units of concentration, and it's understanding that they are units just like any other units, that you'll have a number associated with them. And why do you have different units for concentration? Is because concentration can be concentrated a lot in a volume, or a little bit in a volume. And so depending on how much you have, a lot or a little, you're going to change the units. Just like another way that might be more tangible is understanding time. So if you're talking about a lot of time, you could have the number 5. So a lot of time would be 5 years, compared to a little bit of time, the units would be 5 seconds. Okay, so that's what concentration terms are, if you have a high concentration versus a low concentration. And so that's why there are different units, percent, parts per million, parts per billion. So for these, are the parts per billion are the lowest concentration, and that would be the most dilute. And that's what I mentioned, is typically for water pollutants or air pollutants, you want these to be low concentration. You don't want to have a lot of air pollution or water pollution. And so that's why those units are in parts per million, parts per billion. You want it that way, and it happens to be that there's not a lot of pollutants. Just basically, that's the less than 1% of what's in the air are air pollutants. Compared to the rest of it, there's more of. So there's more of the oxygen and there's more of the nitrogen. So that's more concentrated, and that's why that's used as percent. Okay, so this is key though, understanding that parts per 100 is how many in 10 squared, compared to parts per million is how many in 10 to the 6th, compared to parts per billion is how many in 10 to the 9. So what you're doing is, because you have low concentrations, the parts per million and parts per billion, you have to take a lot larger sample to count how many is in there. So that's 1,000,000 parts to figure out how much is in there, versus 1,000,000,000 parts. That's an even bigger sample to figure out how much is in there. Okay, so this says that parts per million, ppm, is less concentrated than percent, and parts per billion is even less concentrated than parts per million. Okay, so this though is something where it looks like numbers and math, and you don't actually need a calculator as long as you understand these meanings, that parts per million, parts per billion, parts per 100, they all link back to a power of 10. So let's take this, convert 78% to ppm. So ppm, remember, is parts per million, and the million, remember, is 10 to the 6th. But what you have right now is 78%. So what does 78% mean? 78% means that you have 78 parts in 100, or 78 in 10 squared. Okay. So we have this in 10 parts per 10 squared, but we want to get it to parts per 10 to the 6th. Okay, so to get to 10 to the 6th, I'm going to multiply this stepwise, just like I did in the video, times 10, one at a time. So this means it's going to be 780, and that would be in 10 to the 3rd, times 10 would be 78 with 2 zeros in 10 to the 4th. Another times 10 would be 78 with 3 zeros in 10 to the 5th. And then times 10 again would be a 78 with 4 zeros, or 780,000 in 10 to the 6th. And so that means that the answer here is the goal was to get to 10 to the 6th. So this would be 780 with 3 zeros, and the units are parts per million because we wanted to get to how many million of the sample. Okay. So just understanding the meaning of parts per million is getting to, you need to take a million and then find out how many parts are in that. So if we want to convert 0.9% to parts to ppm, parts per million, this is 0.9% is the 0.9 parts in 100, or 0.9 in 10 squared. Okay, so let's do this stepwise to get to parts per million, or 10 to the 6th. Okay, so I'm going to do this one at a time, times 10. And this first step is not going to turn into 90, but it's going to just turn into 9, moving the decimal over 1. So that's 9, and that's going to be 10 to the 3rd. Okay, that's because it started off a decimal. It started off the 10th place. So now it just moved the decimal over. So you have, instead of 0.99. So now this is times 10 is going to be 90 in 10 to the 4th. Times 10 again is going to be 900 in 10 to the 5th. And then times 10 again is going to be 9,000 in 10 to the 6th. And that was the goal, was to get to 10 to the 6th. So what that means is you have 9,000 with the units parts per million, ppm. Is this making sense to you guys? Think you can do this? So let's understand now, going the other direction. This is the convert parts per million to percent. Okay, so first try to picture what it is. Parts per million is the dilute, less concentrated. So you have a big sample and you want to go to percent. Okay, so this is convert the 45 parts per million. So that's 45 ppm is 45 parts in a million, or 10 to the 6th. So we want to get to percent, and percent, remember, is parts per 100, or parts in 10 squared. So you want to get to from 10 to the 6th down to 10 squared. So this time I'm not going to be multiplying, I'm going to be dividing. Okay, so dividing by 10 each time, because I've got to get from 6 down to 2. So dividing by 10 is going to be 45 is 4.5. And that's in 10 to the 5th. And dividing by 10 is 0.45. So move the decimal over, and that's in 10 to the 4th. Dividing by 10 again is 0.045 in 10 to the 3rd. And then dividing by 10 again, had to move that over, is going to be 0.0020 zeros before the 4.5 in 10 squared. So dividing by 10 each time to get to 10 squared, which is parts per 100, or that is 0.0045%. Okay, so hopefully you guys understand why I divided that time, because I was in millions, 10 to the 6, but need to get down to 10 squared, 10 to the 2. Okay, so let's take a look at this next one. So let's understand first, 45 ppm is parts per million. So that means 45 ppm is the same 45 parts in 10 to the 6th. This time, instead of going to percent, we want to go to ppb. So remember, ppb is parts per billion, or parts in 10 to the 9. A billion is 10 to the 9. Okay, so what are we going to do this time? Multiplying or dividing by 10? Well, it is 6. We want to get to 9. So this is multiplying by 10. So this is times 10 for each of these. So 450 in 10 to the 7. And then times 10 again, 4500 in 10 to the 8. And then times 10 again, 45000, 3 zeros. in 10 to the 9. And that's what I was trying to get to, parts per billion, or parts in 10 to the 9. So that means this answer is 45 with 3 zeros, or 45,000, and that's parts per billion, or ppb. Okay, and then let's take a look at this one. So this is convert 45 ppb to ppm. Okay, so first let's understand what is 45 ppb. So 45 ppb is 45 parts per billion. So 45 in a billion, which is 10 to the 9. So what we're trying to get to is parts per million. And remember, parts per million, ppm, is parts, how many parts in 10 to the 6th. Okay, so we want to get to 10 to the 6th. So what is it right now? It's 10 to the 9. So are you going to be multiplying or dividing? To get from 9 to 6, that's going to be dividing. So this is dividing by 10 each time. This is going to be 4.5 in 10 to the 8th. Dividing by 10 would be 0.45, and then 10 to the 7. And dividing by 10 again is 0.045, and in 10 to the 6th. Okay, so I was trying to get to 10 to the 6th. So what that means is this is going to be 0.045 ppm. Okay, so you have each of these answers. Now, one thing you'll notice is I didn't go to a calculator. Okay, I also didn't look at any sig figs. Why not? Because this number, I didn't have any calculation. I'm just basically doing conversion. So this is maintaining sig figs for all of these though. So notice that this number started off 2 sig figs, and it still is 2 sig figs because those leading zeros are not significant. Or this number started off 2 sig figs, 45, and this answer is still 2 sig figs because those trailing zeros are not significant. Okay, without a decimal, trailing zeros are never significant. And then this is 45, which is 2 sig figs, and this answer is still 2 sig figs because the leading zeros are never significant. Okay, so we ended up keeping all those same sig figs because zeros without decimals or leading zeros are not significant.